they were interested. So, good morning, everyone. Today at the topics in Sub-Riemannian geometry, I'm gonna present the hyperbolicity of the affine-additive group. We have a summary to kind of warm up ourselves. We will consider, first of all, the complex plane and the unit disk, their distinction under conformality, try to generalize this as a distinction under quasi-conformality, and this will lead us towards a definition of some sort of, not a complete invariant, but kind of a good invariant for quasi-conformal maps in measured metric spaces. And this is the definition of what is the parabolicity and hyperbolicity. So this kind of distinctions between these two classes of different metric measure spaces, and with different, I mean different under quasi-conformality. And later we will see how this applies to distinguish the Heisenberg group from the affine-additive group that we, I mean, I have this subscript SR over H just to mean that we consider the Sub-Riemannian Heisenberg group. We have already defined both groups and their Sub-Riemannian distances long ago under this kind of reading seminar. So I will not recover the definition of these two metric measure spaces. And as a last thing, we will consider a quasi-regular map from the affine-additive group to the Sub-Riemannian Heisenberg group. Good. So I guess everyone took a complex analysis course, and they remember that every entire bounded function is actually a constant. This is what is the so-called Liouville's theorem. And this allows indeed to distinguish under the conformal lens what is the complex plane and the unit disk. I'd like to add also that this is a great result, but I would like to consider a proof with a different type of method. And I want to see this proof because it's kind of robust enough to not just prove us that these two, so the complex plane and the unit disk are conformally distinct, but also quasi-conformally distinct. Good. So for doing so, I'd like to remind you what is the modulus of a curve family. So we stay currently in the abstract setting of metric measure spaces, and we take a curve family, and we define the set of admissible densities A gamma as the Borel functions from X to the interval 0 plus infinity, where the line integral is larger or equal 1 for all rectifiable curves. And we can actually now define the modulus as the infimum of rho to the power p with respect to the measure of the space, and this integral taken all over the space, where rho is one of these admissible densities. So it's mostly a refresh. I'm gonna go quick on this because we already defined what is a modulus curve family in other editions. And two kind of important properties to remind is kind of the monotonicity of the modulus of a curve family. So if we have a family of curves and which is a subset of another, then the modulus is stable. And if we have two curve families, gamma 0 and gamma, for which for every curve in gamma, there is a subcurve in gamma 0 and gamma 0, then the modulus, the p modulus, is will be less of gamma will be less equal than the p modulus of gamma 0. And what I would like is kind of to put in practice this modulus, and yeah, to do so, I want to do this example together. Two things. When we want to compute it, if we want an upper bound, we can plug any row that is admissible and compute this explicitly, and that gives what is an upper bound. And for kind of a lower bound of this, it turns very useful this first proposition here. So it turns useful, but we have kind of to select wisely a family of curves, gamma 1, which will be contained in our gamma. And so we have the annulus centered in 0 with radii r and uppercase R, and we define as gamma RR to be the curves that connect the two boundary components of the annulus. And what one sees is that the two modulus is actually equal to pi times the inverse of the logarithm of r over little r. And as I said before, one can compute this explicitly by considering this admissible density. And so first of all, prove that this density rho 0 is admissible, and then do the explicit calculation with this rho 0 of this integral, where here we have the Lebesgue measure, here we have p equal 2, and we'll find this as an upper bound. And the lower bound, which will consist of the same number, follows by considering this subfamily of curves, which are the radial curves. So the curves that connect the two boundary components by following a line. Indeed, we are fixing an angle and moving along the radius component. And okay, so we can, now that we have this example in mind, we can move to kind of the next step, which is talking about what is a quasi-conformal map. So I want to give you the most handy definition for today's talk, which is the geometric definition. I take two metric measure spaces of same Hausdorff dimension, and I consider a homeomorphism between them. We say that such map is quasi-conformal if there is a constant larger than 1, for which we have this double-side inequality. We can say that the modulus of the image is preserved by Lipschitzly with the constant k with respect to the modulus gamma. And we want this to hold for every curve family. So now we are in position to conclude why there is no quasi-conformal map between the complex plane and the disk. And we can do it as follows. So let's assume that there is such a quasi-conformal map from the complex plane to the disk. Due to the homeomorphism property, we know that the preimage of the kind of annulus that is in the unit disk centered at 0 with inner radius 1/2 and outer radius 1, well, these will be contained in another annulus, A centered in 0 with radius liter r and outer radius infinity. So these will be contained in this kind of portion of C. And what the previous example illustrated to us is that is that this modulus inequality here is contradicted, because on one side, the modulus of the curve that connect the boundary region of this annulus is finite, while this, we can see that here, to 0. Okay, so we are now in position to define what is parabolicity and hyperbolicity of a metric measure space. And we define gamma EF to be the family of all curves that join the sets E and F in our metric measure space X. And just for brevity of notation, we set the P modulus between E and semicolon F to be the P modulus of the family of curves gamma EF. And we define what is the P modulus at infinity for a subset to be the infimum among all P modulus between E and F, for which X difference F is compact. And we say that a metric measure space X d mu is P parabolic if the modulus will be equal to 0 for all bounded set E subset in X. And we call it hyperbolic if this is not the case. So if it is not P parabolic. Okay. So now what we can do is generalize or try to move what we have learned about the quasi-conformal distinction of the unit disk and of the complex plane to our sub-Riemannian groups, the Heisenberg group and the Affine-Additive group, respectively. So to prove this, we can show it with a proof sketch. And here, what I want to remind you is that the Hausdorff dimension of the Heisenberg group and of the Affine-Additive group is 4. And so kind of the quasi-conformal, so the definition of a quasi-conformal map in the geometric sense will take Q to be equal to 4. So we will try to reach a contradiction where here we have the 4 modulus. And we can do it with 3 steps, essentially. The first one is a proposition, and essentially tells us that if we know the space well enough on the large scale, so if the measure of balls is bounded by some constants times Rn for all points and for R sufficiently large, then we can show that this space X d mu is n prime parabolic for all n prime larger than n. And this type of proposition applies well both for the Heisenberg group and for the Roto translation group, for example. The fact that we know that a large scale balls grows like R to the 4 in Heisenberg group it was known, and like in the reading seminar, I think, of Georgos, he introduced this to us and he proved this to us. A little remark, if we also want to say something on the distinction of the Affine-Additive group and the roto-translation group instead. We can see that essentially R3 acts by isometry that are given, isometries given by the left translations on the roto-translation group. So this essentially tells us that the two groups are quasi-isometric by a result called Milnor-Schwarz theorem. And knowing that these two groups are very compatible at large scale tells us that at some point, also the measure of balls in the roto-translation will be comparable from above, like a constant times r to the power of 3, because that is quasi-isometric to R3. And that is helpful because then we know that both spaces, the Heisenberg group is 4 parabolic, and we know that the roto-translation group is 3 parabolic and also then 4 parabolic, thanks to this proposition. I'm gonna skip the proof of this because it's not the scope of today, let's say, but I'll be open to discuss this later if you have questions. Okay, so this thing is what I discussed so far. And yeah, so this other part is the proof of why is the Affine-Additive group for hyperbolic. And the fact that one space is for hyperbolic and the other is instead for parabolic will be what gives us the contradiction in the quasi-conformality. And so to prove this, we essentially define some subspaces, some subsets, where, so keep in mind that the Affine-Additive group, we can see it as a 3-dimensional space where we have coordinates A, lambda, and T, where lambda and T are the parts of the hyperbolic plane, and R is, A is just a real component. So what we know is that we take a set E that is a square, and here it is in the lambda coordinate equal 1, and on the other we take another set, another square, a sequence of squares, fn's, that are slowly, let's say, approaching the boundary of our space, which is when we have lambda equals 0. And okay, so what I want to show is that the modulus of this curve family is strictly larger than 0. And how do I prove this? Instead of taking all curves that are kind of rectifiable and join the two boundaries, I want to take a particular subfamily of them and compute this explicitly. The family of curves where I can compute this explicitly are the curves that are just moving on the lambda coordinate and fix both the A coordinate and the T coordinate. These curves are horizontal because at least the people who are specialists on the Affine-Additive group remember what is the contact form. And since we don't have any change in the A direction and in the T direction, these type of lines that are connecting our sets are horizontal. And with these lines, the computations can be done explicitly. And one can see that the modulus of this curve family is actually larger than 2 to the 4 over 3 to the 3, which is a number which is strictly larger than 0. So we have this kind of quantitative result, and this tells us that the space is hyperbolic. That's kind of, this is what answers the difference under quasi-conformality between the affine-additive group and the Heisenberg group, or also in the same manner, the difference between the roto-translation group and the affine-additive group. I would like to add a couple of things. So if we would like to kind of see in a more general way how the Heisenberg group and the affine-additive group are related, can we kind of relax the definition of quasi-conformality and let's say try to see them also under this kind of lens? And a good type of definition is the definition of quasi-regular map. And this can be given in a general kind of context, which is the one of Sub-Riemannian manifolds. So we take two Sub-Riemannian manifolds, M and N, where here we have our distributions and the Sub-Riemannian metric associated to the distribution. And we assume that both M and N have same Hausdorff dimension. We define a quasi-regular map to be a continuous map which lies in some sort of reasonable class of locally integrable functions whose also derivatives are integrable, are Q integrable, and we also ask the condition that F is a weakly contact. So this means that the tangent map F sends the distribution dm in the distribution dn almost everywhere. And now we can do a consideration. When we know that the tangent map of F sends the distribution in the other distribution, we can consider the restriction of the tangent map to the distribution related to M. And we call this kind of the horizontal differential. This is an operator that goes from the horizontal distribution of M to the horizontal distribution of the manifold N. And what is kind of helpful is that we have on both distributions two inner products. So we can actually define what is the operator norm, which is visible here. So the maximum among these images of tangent vectors with unit length, let's say, but we can also define the minimum. And when we require that the ratio between them is bounded by a constant for almost every p in the manifold, we actually have the three requirements to say that the map is quasi-regular. But we also want to include another type of maps in this class, which are the constant maps. And to do so, we essentially impose that this ratio, when f is a constant map, so this quantity will be 0, this quantity will be 0. We impose that in that case, this ratio is 1. And this will be also a quasi-regular map. So a constant map is also considered to be quasi-regular. So I can now tell you one first result, which tells us that if we have a equiregular sub-Riemannian three-manifold and a quasi-regular map from the sub-Riemannian Heisenberg group into this manifold, assuming that n is 4 hyperbolic, implies that f is a constant map. And so this actually has an implication in case n is the affine-additive group. So not only we know that these two spaces are quasi-conformally different, but we know that also there is no quasi-regular map from for the Heisenberg group to the affine-additive group. And one also wonder what happens if instead we take the converse. So we take a we assume, so we ask ourselves, is there a quasi-regular map from the affine-additive group to the sub-Riemannian Heisenberg group? And this is so. It's given by this map. Okay, so we have A, lambda, and T, and this is mapped into root of lambda cos A, root of lambda sine A and T. And one can see that the property of quasi-regularity are actually true. One can show that indeed this map is continuous, relies in this Sobolev class. Can see that this map is actually sending the distribution in the other distribution, and can explicitly compute this ratio. And an explicit computation gives that the k is actually equal 1. It's very interesting that kind of if we switch target and the source space, we eventually obtain, in one case, no quasi-regular map. In the other case, we obtain not just a quasi-regular map, but kind of the best type of quasi-regular map, which is the one quasi-regular. And yeah, for me, for today, this is all. Thanks for your time and for organizing the seminar.